All right, hello everybody. So this is our sort of C++ review section here. And we're going to review that by looking at a few different things here. So the first thing we're going to review is a thing called a bag. A bag is a data structure, like a way of storing, objects or items or elements or whatever, that has a couple of sort of like particular twists to it here. Some of the things you might use this for are like, imagine you have an RPG and you want to keep track of all the sort of like monsters that are active. So monsters spawn sometimes and monsters die sometimes. So we want to be able to like quickly add new monsters to the bag of all the monsters that we have. When a monster dies, we don't want it to take like a huge amount of time to remove that monster from the bag there. And then, of course, we need some way of like, looping over all the monsters in the bag and, running their AI or like moving them to new positions or whatever they're like that, right? Similar thing, if we have like a shooter game here, we want to track all the sort of bullets. Any situation where we have a big collection of things and things sort of like get created and destroyed frequently. So we want creating and destroying things to be sort of fast operations. But then, of course, we do need some way to like loop over all the stuff that we have, some way of sort of looking at everything and being like, all right, what are all the things that we have there like that? So here's an example of like what using a bag would look like in C++ here. So up here, we're going to create our bag. This is a variable declaration. So this is the same as when you write something like, int x equals 10. Right, that declares a variable called x and sets its value to 10. Here we're creating a variable named b, and we're passing the value of 20 to its constructor. So for a bag, that number 20, that sets the capacity of the bag. That's the maximum number of things that you can ever store in the bag here. So bags will have a fixed maximum capacity. When you create it, you say, I'm never going to store more than 20 things in here. And then if you try to add more than 20 things to it, we'll sort of decide, what happens in that situation. We add new things to the bag with the insert function here. So we're adding 3 things to our bag. This is just a bag that holds integer values. If you wanted a bag that holds monsters or strings or something, like you could build that based on these same principles. But for the sort of, purpose of keeping this all simple, our bag just holds ints. So I'm inserting 3 ints here. I'm inserting 5 and then 12 and then 7. So at this point, the capacity of my bag B is still 20. That doesn't change, but its size is 3. It should have 3 things in it here. So now I want to loop over all the stuff in my bag and print it all out. So I write a for loop that looks like this. Each of the things in my bag, I assign it like a position number between 0 and size minus 1 here. So if I have 3 things, then I have position 0, position 1, and position 2. So size here, that's going to be 3. Clean that up a little bit. That's going to be 3. So I starts at 0, and I is less than size. So I is going to go 0, 1, 2. And then the at operation down here, you give it a position number at I, and it gives you back the ith thing here. Now here, when we run this loop, it might print out the stuff in the original order of 5, 12, 7. That would mean that 5 is at position 0, 12 is at position 1, and 7 is at position 2. Or it might print them in a different order. It might print them in the order of 12, meaning 12 is at position 0, 7, meaning 7 is at position 1, and 5 is at position 2. Or, it might print 7, 12, 5. So it'll print these 3 numbers up here, 5, 12, and 7. Sorry, that was kind of messy. But the order of them is sort of not necessarily the same as the order in which we insert them. And that's because in the bag data structure, we relax sort of 2 of the usual rules that kind of apply here. We want to make inserting things, and then later on we'll see we can erase things from a bag. We want those to be as fast as possible. Because again, we're spawning monsters all the time. Monsters are dying all the time. We don't want those to be slow operations here. So we allow for the following. Insert and erase can reorder the existing elements of the bag. So when you insert something new, the stuff that was already there might like shuffle around in order to make room for it or something like that. And when you remove something from the bag, the stuff that is left behind might shuffle around as well there like that. So that's why, if I insert 3 things and I loop over the stuff that I have, I don't necessarily get those things out in the order that I put them in. The sort of inserting process might have moved them around and shuffled them to something different than the original order there like that. And again, the reason why we sort of do this is because we want inserting things and erasing things to be nice and fast there like that. The more sort of like restrictions you put on something, the more work usually it has to do, right? So if we said, okay, inserting things doesn't change the order of things, erasing things doesn't change the order of things there like that, those 2 operations may have to do extra work to kind of preserve that sort of property. So by sort of relaxing that and saying like, you don't have to do that, hopefully we can make insert and erase be faster than they would be otherwise there. And again, like the idea is you'll use a bag in situations where you don't care about the order. If you have a bunch of monsters in an RPG, there's no first monster, second monster, third monster. You just have all the monsters. You just need to loop over them every frame or whatever to run their AI. But you don't care which one comes up first, which one comes up second, which one comes up. So, you don't want to use a bag in a situation where you do care about the order of things there like that. Okay, so let's look at assignment 0 is this code that we're sort of building right now. I'm going to give you the solution here. So if you want to sort of follow along here like this, you can set up your assignment 0. You might have already done this if you looked at the FCC size sort of review video there, but you basically create a directory on the server for CS133 assigned 0. Then you'll move into that directory to sort of get ready to work there like that. Now I've made an empty bag HPP file that you can sort of start from there. So this command here will copy that file into your assigned 0 directory. And then you can also copy in the test sort of source file here for it there. You can have that ready to go. The second one here, you don't have to do this. If you just run the test assignment script, it'll grab a copy of that for you. But if you want to look at that test script there or sort of run it manually, you'll need that there. Then we'll create our Git directory. So we'll do, git init. We will do a sort of starting commit here where we will add our first 2 files here, HPP and the CPP file. We'll do a git commit just to say, hey, we're starting assignment 0. And then you can edit the bag HPP file in Micro or whatever editor you prefer in there like that. So we'll write some code in here. And then if you want to test it, you would do Control S to save. And then do Control Q to quit back out here to the shell. And then run the test assignment script. Test dash assignment. And that will tell you sort of what parts of the bag sort of data structure. If you're just copying the code that I'm giving you right now, it should all sort of pass there like that. But you can try, a little bit at a time and sort of see as it passes more. All right. Okay, so what are we going to build this sort of bag out of here? What's it going to look like here? We saw earlier that we declared a variable of the bag type. So that means bag has to be some kind of a type. And the most sort of logical choice is to make bag be a class there like that. Usually when we build a data structure, we're saying we're going to build a class there like that. We need to have a constructor. That's what CTOR is usually sort of like the shortcut for a constructor. And then that will be what sort of takes the capacity and sort of sets up the bag to say hey, this is how much space I can hold. Then we have a size operation that returns the number of items that we currently have. I didn't show it in the example code, but we'll also want to have a capacity operation that returns the capacity. Now, the size goes up and down as we insert and erase things there. Capacity, once you create a bag, that doesn't change. So if you create a bag of capacity 20, the capacity will always be 20 going forward for that particular bag. But because bag is a class, that means we can create multiple bags with different capacities. A bag is full if the capacity is equal to the size. So we'll give ourselves a little shortcut function that will tell us whether or not it's full. A bag is empty if its size is 0. So again, we'll give ourselves a little shortcut function to tell us if it's empty. And then we have the at function that gives us the ith item there. The valid values for i's are, of course, 0 to less than size here. So 0 to size minus 1. For adding and removing things here, we have insert that I just sort of showed you. That will add a particular thing to the bag. And then we'll have an erase operation to remove something from the bag here. Note that there's like an important difference between the two of these. When you insert something, you give the value to insert. So we insert 5, we insert 12, we insert -7 or whatever. But when you want to erase something, you give its position, not its value. So if you want to like remove, 12 from the bag, you have to figure out what position 12 is in, like loop over all the stuff in the bag and figure out where it is, and then erase that particular position there like that. We'll also add a few extra operations here. So we'll have a function that just tells us, is there an X in the bag or not, just true or false. We'll call it exists. We'll have a function that gives us the position, the index where X is, if it's there. Excuse me. Or a -1 if it doesn't exist. And then because it's kind of annoying that I want to remove 12, I have to loop over everything and figure out where 12 is, we will wrap that functionality up into a function called remove. So remove, you give it X. You give it the thing that you want to remove, not the sort of position. So erase removes by index, while remove removes by value. So this will be sort of like the skeleton of our class, right? We have a class, we have a constructor, and then we have all of these like member functions. So this is a skeleton of our sort of class here like this. Box around. I don't know. So we've got our bag, we've got our constructor here. All of these are just declarations. So if they have a semicolon at the end there, they are function declarations, right? We'll have to supply the actual code for them somewhere else. We've got constructor, that's our capacity in there, right? C is the sort of capacity that we want to have. There. And then we've got all these other functions here, size, capacity, blah, 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 all the stuff that was sort of mentioned previously here. So we're basically going to be filling in all these functions here, right? We're going to replace the sort of semicolon there with curly braces with the actual code that goes into each of the functions, one at a time there. If you want to sort of pause the video here, I think if you're starting from the bag HPP that I gave you, this is already in there, but you could, type this into a blank file there or something like that, or just whatever. I'm not your mom. Okay, so there's two ways that we can build a bag here. Two ways that we can sort of put the stuff under the hood in the private data section of the class here. In this one, we're going to build it on top of a vector. So vector comes from the sort of standard library. So that means up here in my bag HPP, we're going to have a hashtag include, right, for the vector header. We can make use of the standard library vector class there like that. So I'm creating a vector of ints here in my private data section. And the way that I'm going to set this up is I'm going to set the size of the vector to the capacity of the bag here like that. So basically I'm going to make a vector of, for example, size 20, but then I'm going to keep track separately in this SZ variable how much of it I'm actually using. I will have a capacity of 20, that will mean the vector will have size 20. So the size of the vector corresponds to the bag's capacity. And then I have this other variable sz that tracks how much of the vector I'm actually. So this is my constructor over here. You give it your capacity, which in our case, for example, is 20. We resize the vector to have size 20. So that means the vector has enough space in it to hold 20 ints. But my sz variable here is keeping track of the fact that I haven't actually stored any values into it. There's still 20 ints in there, right? Like the vector is filled with 20 zeros basically, but I didn't put those zeros in there. Like they weren't inserted by the user. They're just sort of like the default value in there like that. And then when we do an insert, of course, size will get incremented, and when we do an erase, sz will get decremented there. Okay. To make things a little bit easier to visualize, let's reduce our capacity to 8 instead of 20, just so that I can fit it on the actual sort of slide here like this, right? So this is a sort of visualization of what the sort of internals of our bag looks like initially, like just after the constructor is called here. So we have a size of 0 and a capacity of 8. Now the sort of note down here mentions, right, there are actually, zeros in all of these entries in here. Like these are all filled with zeros. But the user didn't put those zeros there. It's not like they inserted 8 zeros there like that. So the size down here tells me that of these sort of 8 spots, I'm not actually using any. Like none of those are sort of user supplied there like that. So these zeros are going to get overwritten as values are inserted here. So the easy methods here are the size method, right? We have that in our sz variable, so we're just going to return that, right? The capacity method here, what? Cap, that's not right. Excuse me. That's wrong. Where's our capacity stored here? It's going to be stored inside of the vector's size, right? So we're going to do data dot size. Empty over here, I could say, if you wanted to, you could write this out as a full sort of if else. You could say, oh, if sz equals 0, return true, blah, 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 like that. But you don't really have to do that, right? Like if you're basically saying if something is true, return true, else if it's false, return false. So we can just say return size equals 0 there like that. And again, instead of doing that, you could just say sz, because what does the size function return? It returns sz over there like that. But I'm going to go with using the size function here. It just kind of makes it a little bit more sort of obvious as to what it is. So when is my bag empty? It is empty when the size is 0. When is my bag full? Well, it's full when the size is equal to the capacity. So that's exactly what I'm saying right here. Whoops, who forgot a semicolon there like that? I got hacked. That's why the semicolon's missing, and that's wrong over there. And again, if you wanted to, you could write this as sz equals, and then replace the call to the capacity function with data.size. But here it's kind of, even more obvious why it's nicer to use the functions. Size equals capacity, as opposed to sz equals data.size. So it's like size equals size. Like, what's that mean here? Whereas if we use the function names, it's kind of obvious. Oh, we're full if the size is equal to capacity here. We'll look at the at functions a little bit sort of later on there and sort of see what that looks like in a second there like that. But I'll be using these in our other functions as well there. Like, this is sort of foundation that our bag is on there. Those are the easy ones, right? Those don't depend on sort of how we implement insert and erase under the hood there. So we can just kind of get those out of the way there. Okay, so let's say that we do an insert here. We do insert 12, and we can say, what's the easiest place? Where's the easiest place to put that sort of 12? And the easiest place to put it is probably like, at index 0. Again, remember all of these like sort of entries here are filled by default with zeros. So I could put that 12 anywhere. All of these sort of spots are available for me to use. So I could put that 12 anywhere in here. But it's easy enough to just sort of put it at like, like at index 0 there like that. And then we increment the size to 1 because now there's one more thing in my sort of bag there like that. Another way to think of the size is it basically tells you what's the index of the next available sort of spot. So right now, the next available spot is index 1. If we insert another thing, right, it's going to go here at index 1, and then size will be 2, meaning the next available spot is at index 2 there like that. In fact, let's go ahead and insert all three things here like that. So if I insert 12, 12 goes there. Then I insert -7, 12 there. -7 goes there. And then 6 goes over here, like that. And then my size is 3. And again, like you can think of that 3 as not just being that there are 3 things here. That is also the index of the next available spot. So if I do another insert, it will go right there. So we allowed the possibility that inserting things might shuffle the existing things around. But it turns out that that's not actually like sort of useful, right? Like if when I insert this 6 here, the easiest thing to do is just drop it into index 2. It would take more work to move the 12 and the -7 around to sort of like make room for the 6 or something like that, than just dropping the 6 in the sort of next available spot there. So even though insert is allowed to shuffle things, it's not actually useful for it to do that. It doesn't make it like, there's no way to make insert faster by moving the other stuff around in there. That adding new things sort of at the end of what we already have is the fastest way to sort of insert them there. So that means if you go back to that sort of like example of using the bag data structure, the order in which that like loop would print out the stuff in the bag would be exactly the same as the order that we put them in there. So it would come out as 12, -7, and then 6. That would be how that sort of for loop would print them out there like that. So here's what my insert function would look like. Right? You give me a value to insert. If the bag is full, we don't want to like sort of go beyond the end of the vector. That would be like really bad, right? So we do a little quick check here to see if we're full. And if we are, we just ignore the insert there like that. We don't do anything with it. And again, remember that the definition of the full function is basically just is the size equal to the capacity. So if you wanted to, you could replace that call to the full function with that. And again, remember, size function is just the same as SZ, and our capacity, excuse me, just comes from size of the vector there like that. So all of those would sort of be equivalent. Assuming that we're not full though, we just drop X into the next available spot. Again, SZ is like the index of the next available spot. And then we increment SZ. If you want to get all fancy like, right, you could make this into a one-liner using the post increment. Like that, right? Because if you do a post increment, put the plus sort of after the thing there like that, sorry, later. It means delay the increment until after sort of everything else in the statement has had its effect there. So that would drop the thing into SZ and then increment SZ after we're sort of done there like that. If you like using those sort of shortcuts, that would be one that into action. A lot of times I'll sort of show you these shortcuts here. I'm not saying you should use them. I'm just sort of like, trying to cover all the bases and kind of give you everything you sort of want. You might want to sort of see in the possible land here like that. So there's our insert. All right. Now we want to do erase. So remember, erase, you give it the position to erase. You give it an index that you want to erase here like that. Let's think about like what would be the easiest index to erase. Easiest one would be like if you asked me to erase the thing at the very end. Like if you said erase 2, which means we're going to actually get rid of 6 there like that. Because what do I have to do to get rid of the 6? All you have to do is decrement the size to 2. I don't need to like delete or actually do anything with the 6, right? The 6 is still there, but if I do another insert, it would overwrite the 6 there like that. So there's no way to delete a particular like individual value out of the middle of an array there like that, or the middle of a vector. All we can do is kind of like, sort of record the fact that, hey, this spot is now available for us to use for something else there in the future there like that. So the easiest place to erase would be the last position there, because we can just decrement the size. But of course, like there's no guarantee that that's what you're going to ask me to erase. You might ask me to erase the thing at position 1 or the thing at position 0. So how do we handle those? Well, if you want to erase something other than the last thing, let's just turn it into the last thing here. Like, let's say that you wanted to, in this case, we're going to erase 0. Right, like that. We want to erase the sort of thing at position 0. We want to erase this 12 there like that. What we're going to do is we're just going to swap that 12 with the thing at the end, with the 6. So we'll turn the sort of more difficult case of like, oh, erase something in the middle or at the beginning into the easy case here. And again, I'm allowed to do that because we allowed for the possibility that erase might shuffle around the other sort of remaining elements there. So we go from having 12, -7, 6 to having 6, -7, 12, right? We did a swap here. So now the 12 here is at the end, and that's the easy one to erase. We just decrement the size, and now it's, sort of quote unquote gone there like that. Now, of course, it's still there, right? Like this 12 is sort of still there after we decrement the size to 2. We still have a 12 in there like that. But that's not really a problem. If we insert another value, it's just going to overwrite the 12 there. So I don't need to sort of worry about the fact that there's old values floating around in the sort of part of the array that I'm part of the vector that I'm not using. If I do need those things, if I do insert into those things there, we'll just overwrite them with the sort of new values there. Like, if you wanted to, you could write a 0 in there or something like that, but you don't have to, right? We can leave the 12 in there. If we ever need it again, we'll just overwrite it with whatever the new value is. So my final array, after doing like the erase for sort of position 0, which was 12, right? This erase 0 here means we're trying to get rid of the 12 that was originally in that sort of position there like that. After we're done, the contents of my bag are 6, -7. So our original contents were 12, -7, 6. And then after the erase, they are 6, -7. The 6 changed position. It went from being at the end to being at the beginning there. The -7 didn't move. Like, we allow ourselves the possibility that everything might shuffle around here, but it's only really useful for the thing that we're erasing and the last thing to sort of shuffle around in their positions. So based on that, here is what our erase method looks like. We're given a position number in I, and again, remember the restrictions on I are that I has to be greater than or equal to 0, and it has to be less than the size. If you give an I that doesn't fit those criteria, it's like an out-of-bound index here. So that's just what we're doing up here, is we're checking for that sort of requirement. And again, like, you know, you can handle this any way you sort of want. Like maybe we should throw an exception or something like that. But in this case, just for simplicity's sake, we're just returning. If you give me an out-of-bounds index, we just ignore it. Don't do anything there. Otherwise, we just use the standard library swap function to swap the ith thing with the last thing, and then decrement the size. Two simple operations that just like sort of move a couple things around here. There's no like looping necessary or anything like that. So removing things, provided you know where they are at, you know their positions, their indexes, should be sort of fairly fast, right? One thing to notice is if the size is 0, right? If the thing is empty, so imagine that this size here is 0, then this condition here is just always false. So if you have an empty bag, you can't erase anything from it. It just sort of hits the return immediately. All indexes are out of bound there. So that's just what this little note down here is saying. If you have an empty bag, then it doesn't matter what you erase, it's not going to do anything there. And for our other operations, those do involve some looping, right? Like if I don't know where something is, because of the fact that insert and erase sort of shuffle things around, the only way to figure out where a particular thing is to loop over all the things and check each thing and be like, are you an X? Are you an X? Are you an X? Like that right there. So that's just what this loop does. Again, all my positions for I are I has to be greater than or equal to 0, and I has to be less than size. So this loop is just looping over all the positions between those two things there. If the ith element is equal to X, then that is the position where X is, so we return I. If I get all the way to the end, then we return -1 to mean that there were no X's, right? We couldn't find an X in there. And one little note I'll make about this here, right? There is sometimes a temptation when you see an if like this here, right, to add an else on it. And say like else return -1 or something like that, right? But that's wrong. If you put that on there, what will happen is when I is 0, we'll say, is the first thing X? If it is, we return 0, that's fine. But if it's not, we will immediately return -1. We won't look at position 1, position 2. Remember that return ends the function immediately. It doesn't sort of let the loop continue to run here. So the appropriate place to return -1 is after the entire loop has finished here like that. We have an if without an else in here. If I see an X, I can say, hey, I found an X. Here's where it is there like that. If I don't see an X, I still need to check the next thing and the next thing after that, and the next thing after that, and sort of like keep looking at the rest of the stuff there. Only if I've gone all the way to the end can I actually return -1 and say, okay, it doesn't exist. There's a little sort of like quiz question down here. Could we use the sort of ranged for loop on the data vector there like that? I'll tell you right now, the answer to this is no. But you want to sort of like think about that and sort of understand for yourself, like why is that not a valid thing to do, to loop over the entire data vector there like that? You know, hey, look at that. I forgot I had sort of mentioned this in here. Yeah. So yeah, don't put this else in here like that. It'll sort of exit too early there. Once we've got find written, remove becomes easy. Right? So you give, remove takes an X, and you say like, I want to get rid of X wherever it is sort of is in here. So all we do is we call find, and find tells us where X is. And then whatever that does, we give it over to erase and say, hey, erase the thing in that particular position there. So I could, you know, write all the code for removing something in here with the loop and everything, but I can just build it on top of the two functions that I already have, and then remove just becomes this sort of nice one-line thing like that. So when you're building something like this, you want to think through like, all right, what are the sort of, you know, foundational operations? and then what are the things that can be built on top of them. You don't want to write each function like completely independently. You want to sort of start from the ground up and then build up there like that. Like that'll sort of simplify, your other functions, build the sort of foundational one first here. Note that this still works even if there are no x's. Right? If x does not exist, what will find return? Find will return -1. What happens if you give a -1 over to erase? Well, our implementation of erase ignores negative indexes. It just returns immediately. So it will sort of do the right thing in that case here. It just won't remove anything there like that. Sort of a happy little accident, as Bob Ross might say. And likewise, our exists function, how do you check to see if something exists? Well, find will give me a -1 if it doesn't exist. So all we do is say we find it. And if it's not a -1, that means it does exist. And if it is a -1, that means it doesn't. And again, like if you wanted to, you could write out the sort of full if else in here. You could say if find x not equal to 1, that means it does exist. So we're going to return true. Blah, 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 like that, right? But you're basically saying if this is true, return true, else if it's false, return false. So why don't you just return the thing that is true or false, which is what we're sort of doing. It's not wrong to use the if else or anything like that. Like there's nothing bad about it there. It's just a little bit sort of shorter and tidier to just return the thing sort of directly there. All right, so to sum it all up here, right, our insert works by adding x to the sort of end of the bag there like that. So that means that insert actually does not shuffle, right? Insert preserves the order of the things that are already in there like that. Erase swaps the value at index I with the last value there and then decrements the size. So that means index I and the last index, size -1, get sort of changed, but the other elements remain in the sort of same place there like that. None of the other operations change the element order, right? Like insert and erase are the only ones that sort of like modify the stuff in the bag. Everything else just sort of leaves stuff like as it is there like that. So those are the only two that can sort of shuffle things around in there. Yeah, so that's the basic of our sort of like bag data structure here. The vector class is doing a lot of the sort of heavy lifting for us, right? It's kind of managing memory and doing all of that sort of stuff there like that. So in the next video, or depending on what order you watch them in, I guess it might be the video they've already seen. But in the other video on the bag data structure, we'll do a sort of dynamically allocated array. We'll build the sort of like the storage for the bag ourselves there. And we'll look at how that sort of forces us to think about like memory management and like the sort of special member functions and stuff there. It'll add like, 50-ish lines of code to our bag implementation to basically do all the stuff that the vector class is currently doing for us there. But at this point, you should be able to take the code that I gave you in this video and dump it into your bag HPP in your assigned 0 directory and have it pass all the tests. Like the test assignment script, when you run it, should say everything works the way that it sort of should work there like that. So that's it for the vector-based bag.